In this lesson, we are going to be looking at ways that you can add, subtract, multiply, divide functions, and then do composite functions, which is where you plug one function into the other. And you've done all of this before. It's just that when we've done it before, we haven't paid a whole lot of attention to what the domain should look like as you're doing this. And so we are going to pay a little bit closer attention to those things today, okay? So first of all, you can see some rules on here, and maybe it's a little bit blurry, but you should have them on your sheet that are a little bit clearer. If I am asking you, in this case right here, to add two functions together, that's all I'm asking you to do. You just literally take each function separately and add your two answers together. Paying attention, of course, to the domain. If you're going to subtract them, you take each function and subtract them. This is asking you to take f times g, so I would take function f and multiply it by function g. And this is asking me to take f divided by g, which is, again, to take function f and divide it by function g. The tricky part to this is paying attention to the domain as you go along. Okay, so we're going to do a couple of examples here, and hopefully this will help clear it up a little bit. We are going to, first of all, take these two functions. F of x is x cubed, and g of x is the square root of x plus 1. And we are going to do some operations with them. Add, subtract, multiply, divide them, all kinds of good things, okay? So the key to this is that when you do this, you kind of have to look at the domain of each of these functions separately, and then what your domain would look like once you do the operation on them, okay? So if we look at function f right here, and I'm asking you to take a number and cube it, and you can certainly put this in on your graphing calculator if that helps you, but there is no number that I can't plug in for x. I can take any number, plug it in for x, and cube it. I can cube fractions, I can cube decimals, I can cube positives, I can cube negatives, I can cube square roots, I can cube things like pi and I and all kinds of things. There is no number that I cannot cube. So for f of x, the domain is really negative infinity to positive infinity, or all real numbers. If you graph that on your graphing calculator, a cubic function looks something like this, and you can hopefully tell that way too, that your domain is all real numbers. Okay, for g of x, when you look at that, you cannot have the square root of a negative number, okay? So if I can't have the square root of the negative number, the smallest number that can go inside the square root symbol is 0. So I need to figure out what would I plug in for x to make that quantity be 0. And it would be negative 1. And you need to plug in numbers then that are negative 1 or bigger, so that underneath the radical I get a number that's at least 0. So right here I'm limited to negative 1 to infinity. Okay? So those two things, when you put the function together, kind of get inherited as you carry it around. So I know that when I add f of g of x, I am going to take x cubed and I will add the square root of x plus 1. And this piece gets inherited right down there. So I know that my domain of this entire function, when I add them together, has to be at least that. And I may need to place even more restrictions on it based on what it looks like when I simplify it. In this case, I can't simplify x cubed plus the square root of x plus 1. So this is a function that I get. And my most restricted domain gets inherited, so I know I have to be restricted from negative 1 to infinity. And I have no more restrictions that I need to place on it, and we'll do a couple where you do have to, so I'll show you that in a minute, but for now we're good. Okay, when I subtract, again, I'm going to take x cubed and subtract the quantity x plus 1. I just want to caution you that sometimes you're going to have something like x squared, and if I had to subtract x cubed, if I had to subtract, I don't know, x squared plus 3 or something like that, you would want to distribute this negative through, and that's a common mistake that people make in this particular example. I don't need to do that, but if you're subtracting two functions, you would want to distribute the negative through to simplify that, just so you know, okay? Again, this piece, when I inherit the domain, is from negative infinity to positive infinity. And this piece, when I inherit the domain, has to be from -1 to infinity, okay? So this is my function right here that it looks like when it's simplified. And my domain for that function, again, will have to be from -1 to positive infinity, okay? And here we're just going to simply multiply them. So I will have x cubed times the square root of x plus 1. And there's no other simplifying that you have to do. Sometimes, of course, you're going to end up FOILing or distributing or whatever, depending on what your two functions look like. But this is telling me to take function f and multiply it by function g, which I did right here. Okay? Don't expect you to do anything else. Again, this gets inherited as negative infinity to positive infinity. This gets inherited from -1 to positive infinity. And since there's no other simplifying that I need to do, there's no other restrictions that I need to place on these functions. Okay, here I have f divided by g. So in this case, I will have x cubed over the square root of x plus 1. Okay, now, in this case, this can be all real numbers. Okay, we know that. However, this, as itself, is from -1 to infinity. However, since it's in the denominator, it can't actually be exactly -1, because if it was exactly -1, I would have the square root of 0, which is 0, in the denominator, and you can't have that. Okay, so I need to place an even stricter restriction on this once it's simplified. So this is going to become x cubed over the square root of x plus 1, but my domain has to be bigger than -1 to infinity. And by the way, I noticed that when people think that it's bigger than -1, it has to jump automatically to 0 to the next integer. But it doesn't, okay? Bigger than -1 means that it could be -0.9999999. It doesn't, if it has to be bigger than -1, it doesn't have to go all the way to 0. And that's a mistake that I've seen some people make, so I just wanted to mention that. Okay, that's what that would look like. And then this is asking me to just simply take g times g, okay? I know that I'm already limited from -1 to infinity based on what those domains of each individual function are. If I simplify this, when you take the square root times the square root, this is really the square root of x plus 1 squared, if you can picture that. And these two things cancel each other out, and I just get x plus 1. And it looks like you could be able to plug any number in for x that you wanted right now. Okay, I could plug in positives, negatives, zeros, whatever. The way this function looks, that's what it looks like you should be able to do. But again, the domain, the restrictions of the domain are inherited from each individual function first, and you're going to put the most restrictive domain on it, and then once you simplify, you might even need to add more restrictions. In this case, I don't, but I am restricted from -1 to positive infinity. Okay? All right, then we're going to look at composite functions, which is where you plug one function into the other. I know you have seen this notation that's in the red before. You read it as f of g of x, and either way you write it. Sometimes they put the little circle in there, sometimes they put it in parentheses. Either way you write it, it's read f of g of x. And again, things get inherited, and I'll kind of show you how this works, okay? So, if I'm wanting to find f of g of x, basically that means I take an x value. I first of all have to put it into function g, so I'm restricted by whatever domain I need to for function g. Then I take that answer and I put it into f, and I might even need to place some more restrictions on it. Okay, so here we go. We're going to do this. In this case, if I look at function f is 2 to the x, I can take 2 to any power I want. I can take 2 to a whole number, 2 to a fraction, 2 to a decimal, 2 to positives, 2 to the negative power. I can take 2 to any power that I absolutely want at all. So my domain here would be negative infinity to positive infinity. Okay, and on the other side, g of x, my function is restricted to, again, -1 to positive infinity, like we talked about in the last example. Okay, when you have this right here, f of g of x, and by the way, it could also be written as f of g of x. It means the same thing, okay? And you always work inside out, or actually right to left on these, which seems like it's a little bit confusing. So what I'm going to do here is I'm going to start with function g, which you can see my domain is already restricted to -1 to positive infinity. I'm going to take that and I am going to put it in to function f. Okay, so what this is going to look like is this. It's going to be 2 to the square root of x plus 1 power, which I can't do any simplifying on. But because I started with function g, and I was already restricted to -1 to positive infinity, that I can't lift those restrictions at all when I plug it into the next function. So I'm already restricted to that. And then sometimes you need to add more restrictions to it, but I don't have to, because as long as I know that this is a positive number, I can take the square root of any number, and I can take 2 to any power. So I don't need to add any more restrictions than that. Okay? All right, and now we will go the other way around. And again, it can also be written like this. You might see it like that. It means the same thing. Okay, just different notation. This time you're starting with function f, and function f has no restrictions on the domain. I can take 2 to any power at all. So right now my domain is just from -infinity to positive infinity. But then I go ahead and I plug it in here, and I have 2 to the x power plus 1. Okay, and now you need to think about, now that it's underneath a radical, do I need to place more restrictions on it? And the only way you would need to place more restrictions on it is if you could get a negative quantity underneath the radical. But 2 to any power you could ever have, 2 to the 1, 2 to the 1/2, 2 to the -1. If you remember, 2 to the -1 is 1 over 2 to the 1. 2 to the -2 is 1 over 2 squared, or 1/4. So there is no number, like 2 to any power at all will always be a positive number. It might be a fraction, it might be a really small number, but it will always be a positive number. And then when you add 1 to it, it's going to be an even bigger positive number. Okay, so because of that, I don't need to replace or to place any more restrictions on this than I already have. So this is just simply going to go from -infinity to positive infinity, and that's all I need to do for this one. Okay, and then sometimes you have specific numbers to plug in, which is what these two look like here. Okay, this is telling me to take the number 4 and first of all plug it into function f. So f of 4 would be 2 to the 4th power, which is not 2 times 4. It's 2 times 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16. Then you're going to take that number and plug it into function g. So I will take g of 16, which is the square root of 16 plus 1, which is the square root of 17. Okay, can't simplify anymore. And then on the other one, we'll go the other way around. And by the way, this could also be written as f of g of 2, just so you know it means the same thing. But it first of all wants me to take 2, plug it into g. Okay, so g of 2 would be the square root of 2 plus 1, which is the square root of 3. And then it wants me to do that and plug it in to f. So f of the square root of 3 would be 2 to the square root of 3 power, which I don't expect you to get a decimal or anything for that. We can just leave it just like that. All right, and then this is asking you to figure out which of the ordered pairs are in the relation that's defined by x squared y plus y squared equals 5. All I want you to do is plug these numbers in. This is an x value, this is a y value. Again, this is an x value, this is a y value. It wants you to plug them in and see if they work. Okay, so we're going to first of all plug 2, -5 in. All that means I'm going to do is I'm going to take x squared, which is 2 squared, times y, which is -5, plus y, which is -5 squared, and I'm going to see if I get 5, which it says I'm supposed to right here. Okay, so let's check to make sure that we get 5. So here, 2 squared is 4, times -5 is -20, plus -5 squared is 25. And so I do get that 5 equals 5. And it does equal 5. So yes, this is in the relationship. In the relation, I should say. Yes, it's in it. Okay, if I test 1, 3, then I will do 1 squared times 3 plus 3 squared. 1 squared is 1 times 3 is 3. And then 3 squared is 9, and I get 12. And 12 does not equal 5 like it says it's supposed to, so this is not in a relationship. Okay, and then we'll test 2, 1. And 2, 1 is 2 squared times 1 plus 1 squared. 2 squared is 4 times 1 is 4. Oops, this should be a plus sign. Plus 1 squared, which is 1. And again, I do get 5. So it does equal 5. So yes, it's in it. Okay, then the next question it asks us is this a function? And remember that a function has to pass the vertical line test. So if you were to think about plotting the points 2, -5 and 2, 1, it would not pass the vertical line test. I didn't draw that very straight, but it would not pass the vertical line test, okay? The same x value cannot have different y's, so it is not a function. Okay? So that is that. And then the last thing we're going to look at is implicitly defined functions. This equation right here, x squared plus y squared equals 4, is the equation for the circle that you see. It's centered at 0, 0. It has a radius of 2, and that's the equation for a circle. The problem is that a circle is not a function. So if we want to write these as functions, what we do is we write them as 2 separate functions, okay? If we wanted to be able to graph this on our graphing calculators, we would have to have that equation solved for y. And so if we solve it for y, we would get these 2 equations right here, okay? And the left-hand equation is the top half of the circle, and if I have just that top half, it's a function, and then the right hand is the bottom half, and if I look at just the bottom separately, it's also a function. Put together, it's not a function, but if I define them as 2 separate functions, I still get a circle, okay? Which is kind of what we're going to look at here also, okay? So it says describe the graph of the relation x squared plus 2xy plus y squared equals 1. If we wanted to put that into our graphing calculators, we would have to have that solved for y. Right now, it is not a function itself, but I'm going to make it 2 separate functions so that separately they are a function, okay? So the left-hand side of this equation will factor as x plus x, y plus y, plus and plus, like that. And then that becomes x plus y squared. And I want to solve this for y, so I want to get y by itself. So I will square root both sides, and I will have x plus y equals either positive or -1. So then y will be negative x plus or minus 1. What that means is that y could be negative x plus 1, or y could be negative x minus 1. And these are your 2 implicitly defined functions, where if you look at them separately, they're a function. If you look at them together, they're not, okay? And that's the deal. So hopefully that will get you guys what you need today, and I will see you soon.